Today I'll be solving LeetCode 36. The problem statement reads, determine if a 9x9 Sudoku board is valid. Only the filled cells need to be validated according to the following rules. So here we must ensure that each row has unique digits, and so does each column, and each of the sub boxes that are of sizes 3x3. And the note again reinforces that we should only look at the filled cells, and we don't need to necessarily solve the Sudoku board. We just need to make sure if they follow the 3 rules or not. So let's have a look at the constraints. So the board length and width is always going to be 9x9, and the digits are always valid, so from 1 to 9, and the empty cell is represented using period. What I'll do here, since it's brute force approach, I'm going to go and look at the first row. So my first row elements are 5, 3, 7. I'm going to keep them together, and then I will take my first element and compare it with the rest of the elements in my list. That is, I have 5. I'll compare it with 3 and 7 to see if they are equal. Since they are not, I can say that hey, 5 is unique so far, and then I'll look at the second element, that is 3, and I'll compare it with again the rest of the list here. So I'll compare it with 7, and then I'll say okay, the elements here are unique, hence the first row is valid. So what's the time complexity just for this piece of logic? So let's say we have n elements. So I am accessing n elements. For each of the n elements, I am comparing it with worst case, again, n items in the list. So it's going to be big O of n square. And key constraint that comes to play is the board is always 9x9, right? So the n is fixed. So this can translate into big O of 1 for this problem. And let's look at more optimized solutions. We can use something called hash sets. What we're going to do is, again, we'll take a matrix. You can just imagine the matrix. So we'll have 9 sets, okay, representing each row. For this, let's walk through the same example of 5, 3, 7. These are the first row elements. What I'll do is I will store 5 here. So when I access the second element of the row, I don't need to compare it with other rest of the list again. I can just look into this set saying, okay, so in row 1 I have seen 5 so far, and if it's not there, I'm going to add 3 to my set and then continue. So we have constant lookups in terms of hash sets, so that's going to make this solution optimized. If our input is growing with n, and since we have fixed input size, that is 9x9 for this problem, again, it's just going to decrease our runtime. So we'll do the same for column as well, and think of it this way. So we'll have 9 columns and 9 sets. the logic for boxes. So our goal here is to have again 9 hash sets for these 9 boxes. Okay, let's look at the first box here. I'll divide the row indices by 3, so it ranges from 0 to 2. I'll always get a quotient of 0, and for column again 0 to 2, I'll get a quotient of 0. So let's look at the second box. So 0 to 2, quotient column ranges from 0 to 5. Here if I divide these numbers by 3, I'll get the quotient of 0. If I divide these numbers by 3, I'll get 1. When I say divide, I always mean integer division by default. So let's try for, you get the idea, right? So let's just try the same for, let's say, box number 6. Here the column will range from 6 to 7 and a row will range from 3 to 5. I was looking at this area. So what could the quotient be? Here it's 1 and here we'll get 2. Is there any way we can use these numbers to represent these boxes? So when we add them together, 0, we get 1 here and we get 5 here. So you can see that these numbers are like offsetted by 1. So box number 1 will always have 0 quotient when you add them together. And this is for box 2 and this is for box 6. You're welcome to try any number and see and work it out for yourself. So what I'm going to do is let's just generalize the formula. I'll take ith row, I'll divide it by 3. I'll take jth column, I'll divide it by 3. I messed up. It's not 5 here. It's 1 plus 2. Should be 3, right? In order to make sure that we get unique sum, we'll multiply the row by 3. So now we get 5. So why did I multiply it by 3? Here, let's say we have 0, 0, 0, 1, 0, 2, then 1, 1, 1, 2, 1, 3. To make these unique, and I know that if I multiply 0 by 3, I'll get 0, so that when I add them together, I'll get 1, 2, and 3. Sorry, I'll get 0, 1, and 2. And I want these numbers to continue. What do? I multiply these first numbers by the number of boxes in the previous row, 3. So that's when I get this offsetted number. I know it seems complicated at first, but when you play around with the mod idea and you just think too hard with the indices, that's when you arrive at this. To be honest, I also took a lot of time to get there, and once I understood the solution, I could see why it was the way it was. So yeah, this is the generalized formula for each boxes. Now let's code this up. For ij and range of n. When I say n, it's just going to be 9. And if board of I and j is equal to period, then we can skip. If not, then we should continue. So we'll make sure it's not empty. We'll prepare the row lookup like this. Column lookups, columns and boxes here. So what it's going to look like, it's going to look like 9 sets in range of 9. And set for range of 9, set for 9 indices. I call this boxes. So if our current cell is not empty, then we will add this. We'll check if it exists in row, boxes or columns. Before that, we'll find the box index by using the generalized notation. So we'll take I, we'll divide it by 3 and get the quotient, and then again scale it by 3, and we'll add the offset using the columns. So we'll add the column index and we'll call this an index. We'll see if board of ij that has a current number is in rows of index I, or board of ij in columns of j, or board of ij is in boxes of index. If it's present, we're returning false. If not, then we'll add these set numbers. Dot add board of ij, and we'll do the same for columns and also boxes. So we'll do cols and boxes here. And just a keynote here, we'll store the row in the corresponding row index. We'll store the column information in the corresponding column index, and we'll store the box information in the corresponding box index. So we'll have to reflect the same changes here. Index. So let's say we go through a for loop and we never encounter any duplicates. What do we return? We need to return true. So we'll look at the edge cases now. Let's say we encountered all dots. That means the board was empty. Then it does follow these rules, right? So let's think, yeah, I think this should work because we'll just be skipping this for all of the cells. Let's run this. Okay, so let's see what the top solution says. Continue for box. Wow, okay, so they've just stored box index like this. Default dict set. Nice. So they've used the indices as is and they didn't scale it. So that's one smart way to do it. And I think this is a lot easier than whatever I did. Yeah, that's fun. Okay, great. Let's talk about time complexity again. This is big of one for the problem that's given here. And if the length varies, then it is big O of n, where n is, like greater of the, I would say where n is either the length or breadth of the Sudoku board. Yeah, so that's it. I learned something new and I hope you did too. Thank you.